Okay, so this is section 7.4, which is called basic equations, basic trigonometric equations. So in this section, we're going to be solving equations for angles. So the idea is that we're going to be getting answers that are angles. And this is different from the previous sections, the last couple sections, because we're not verifying identities, we're solving equations. So an identity is an equation that's true for all angles, whereas an equation is just true for a collection of angles, like not infinitely many. Well, it is for infinitely many, but not for every single angle. Okay, so let's start with example 1. They ask us to solve the equation for all solutions. Solve the equation. I'll call this part A. Sine of theta is equal to 1/2. Okay. So we definitely know that this is one of those nice coordinates that will yield a nice angle if we draw a reference triangle or just look at the nope, it wouldn't be that one, it would be this one. Just looking at the unit circle. This is theta, and we've got sine of theta is equal to 1/2, so I've got the opposite over hypotenuse set up, and this is a pi on 6 angle, pi on 6, but I also know that this is satisfied in quadrant 2, where the triangle is oriented this way, theta, this is 1, this is 2, and this is negative square root of 3, so I can get another angle, where sine of theta is equal to 1/2 at 5 pi on 6. So those two angles are happening here and here. Pi on 6 and 5 pi on 6. Okay. So whenever you're finding solutions to a trig equation, the first step is to find all the solutions within one cycle of sine. So first step is to find the solutions, or find the angles that satisfy the equation within one cycle, or one period, within one period of pi, or a period of sine, which, by the way, one period of sine is 0 to 2 pi. 0 to 2 pi. And these are the only two angles that do this, because there's no angles down here that will give us sine of theta is equal to 1/2, because down here it would be negative. So these are the only two angles. But we want all the angles that satisfy this equation. All of them. Not just in the first cycle. The first step is to find all the angles within the first cycle that satisfy this, but the second step now is to add all rotations. In other words, add multiples of 2 pi. I should say add integer multiples of 2 pi to each angle. Because if pi on 6 satisfies this equation, then if I rotate all the way around again and go to 2 pi plus pi, 13 pi on 6, all the way back around, 13 pi on 6 would also satisfy this equation, because I'd be back in the same location. And every single rotation is landing at that angle is going to satisfy this equation. And similarly for 5 pi on 6. The first one does, and then if I rotate it all the way back around, that new angle would, as long as I keep landing either here or here. And the way I notate that is I say theta is equal to pi on 6 plus Now I want to add multiples of 2 pi, so I say 2 pi times k, where k is an integer, and the other one, theta, is equal to 5 pi on 6. So this is every rotation for the pi on 6 angle, and now the other angle pretty much looks the same. Just adding 2 pi times some integer multiple to each one. So when k is 0, we just have our base angle. And when k is 1, that's 1 rotation. When k is 2, that's 2 rotations. When k is negative 1, that's a rotation going the opposite direction. When k is negative 2, that would be 2 rotations going the opposite direction. And traditionally, we actually write this as pi on 6 plus 2k pi. We just tend to write the pi at the end. So that's how I'll write it from now on. So this would be all solutions to sine of theta is equal to 1/2. Okay. So how about cosine of theta is equal to 1/2? Same instructions, find all solutions. Cosine of theta is equal to 1/2. Well, we need to find the base angles where cosine of theta is equal to 1/2. I should expect to get two angles out of this. The first one will be pi on 3, because if I look at my unit circle, I see that this coordinate up here at pi on 3 gives me the x-coordinate is 1/2, or draw your reference triangle. There's 1, square root of 3, 2. And this angle is a pi on 3 angle. So pi on 3. And then what is the other angle that satisfies cosine of theta equal to 1/2? Well, it has to be somewhere where this will still be positive, right? So it's not going to be like this one over here, because cosine is negative over here. And it can't be down here, because cosine is negative down here. It has to be over here. It has to be over here, which corresponds to this reference triangle with a 1 and a 2 and a... Oh, no. This is the negative square root of 3, and this is the 2. So this one will also yield a cosine of theta equal to 1/2, which, and what is this angle? It's 5 pi on 3. 5 pi on 3. And you can see that just by looking at the unit circle. Okay. So my two full solutions then will be pi on 3 plus 2k pi, because I want every rotation, not just these base angles, not just these two base angles, but I want every rotation of each one. And I'm still adding 2 pi, multiples of 2 pi, because cosine of theta, the cosine graph, has period 2 pi, just like sine. So there are those solutions there. Okay. Example 2 says it's just another trig equation, but it says to list 8 specific solutions. So we have cosine of theta is equal to negative square root of 2 over 2. List 8 specific solutions. So they don't want the whole list of infinitely many. They want 8 specific solutions. Well, let's get the base angles first. So square root of 2 over 2, that's one of those nice coordinates at a 45-degree angle, or pi on 4. And where cosine is negative, that's going to be this one and this one. That's going to be 3 pi on 4 and 5 pi on 4. Okay, so 3 pi on 4. So we've got theta is equal to 3 pi. If I listed all of them, it would be 3 pi on 4 plus 2k pi. And theta equals 5 pi on 4 plus 2k pi. This is all of them, but I want 8 specific ones. So theta equals, how about 3 pi on 4, 5 pi on 4. That's when k is equal to 0. K is equal to 0. These are the base angles. These definitely satisfy this equation. Now, so this is when k equals 0. Now, how about when k is equal to 1? Well, when k is equal to 1, I'll add a whole rotation to each one of these angles. So a whole rotation meaning a whole 2 pi. So 2 pi is 8 pi over 4. So I'll get 11 pi over 4 for this one. And then this one will give me 13 pi over 4. Okay, so that's when k is equal to 1. Okay, now I need to add another rotation, so let me let k be 2. And the next one will be adding 8 pi on 4 to each of these, so I'll have 19 pi on 4 and 21 pi on 4. This is when k is equal to 2. So base angle, 1 rotation, 2 rotations, and now down here, I'll just keep going down here. I'll add another 8 pi on 4, which is a full rotation, to each one of these, and I'll get 27 pi on 4 and 29 pi on 4. And that's when k is equal to 3. So I've got the base angle and then 3 rotations. By the way, I could use negative k values. I could subtract 2 pi from these base angles, go the opposite direction to get clockwise rotations. I could do that as well. I just chose to stick with positive values. It's just because it's easier. It's easier to add 2 pi than to subtract 2 pi. Okay, let's do one where the angles are not special angles. So where we're going to have to use the calculator. So pretty much same instructions, except in this example, we're not going to have nice coordinates that yield nice angles. Okay, so we have cosine theta is equal to 0.65. This is not a special angle, or well, this is not a special coordinate, like 1/2 or square root of 3 over 2 or square root of 2 over 2. It's just some random coordinate. So this is not going to yield a nice angle, so we need to use the calculator. And what do? We say, well, if cosine theta is equal to 0.65, then theta is equal to cosine inverse of 0.65. And then use the calculator to say that theta then is approximately, and you'll want to make sure that your calculator's in radian mode to do this, 0.86 radians. 0.86 radians. That's one of the base angles, but there should be 2. So cosine is positive here. We're getting a positive cosine, so we're somewhere over here with this theta is equal to 0.6 radians. That's somewhere, let's see, this is somewhere over here in the first quadrant. And where is the other angle going to be for cosine to yield a positive value? Well, it's got to be down here somewhere, symmetric over this axis. So how do I find this? How do I find this angle all the way around, this one here? Well, I'll say 2 pi minus 0.86, because this is 0.86 here, radians. And I want to go from here, from the x-axis, all the way to this angle. So I'll take 2 pi minus 0.86, and that's going to give me 5.42 radians. So this angle all the way is 5.42. So those are my two base angles. Theta is approximately 0.86 and theta is approximately 5.42, and then I'll add all of my rotations plus 2k pi to each one. Because in the instructions for this example, we want all solutions. We want all solutions. Okay, how about another one? Sine of theta is equal to 0.87. So you're going to want to be careful in the homework to see whether or not they're asking for all solutions or if they're asking for solutions within just some domain. Like if they say find all solutions within 0 to 2 pi, then you would just list the base angles, just the base angles. But if they say find all solutions, you would list the whole thing. Okay, sine of theta is equal to 0.87. So this is going to run similarly to this one. So the first thing we'll need to do is actually find the angle, at least approximately, by using the inverse sine. And this will give us that theta is approximately 1.06 radians. Okay, so that is roughly right here. How do I know it's here? Well, radians, this would be, all the way across would be pi radians, which is like 3.14, so this is 1.57 right here, half of a pi. So for 1 radian, it's somewhere, maybe a little bit further, but it's somewhere in the first quadrant. Where's the other base angle going to be? Where else is sine positive? Well, up here. So how do I find this angle? Well, I'm going to take pi. So I want to go from here all the way to here. So this one is 1.06. And I want to go from the x-axis all the way to this one. So I'll take pi and subtract 1.06. And that's going to give me 2.08 radians. So those are my two base angles, 1.06 and 2.08 radians. So for my full solutions, I'll say theta is approximately 1.06 plus 2k pi, and theta is approximately 2.08 plus 2k pi. Okay. Now, sine and cosine don't always have two base solutions. They don't always have two base solutions. The only time they won't is when you've got, like, sine of theta is equal to 1, or cosine of theta is equal to 1, because there will just be one solution for that. I think I'm going to talk about that. Yeah, I'm actually going to talk about that in a second. Okay. So, example 4. Now dealing with tangent of theta, which is a bit different. It's a bit different in a few ways. First of all, tangent has period of length pi, not 2 pi, and it goes from negative pi on 2 to pi on 2. So not from 0 to 2 pi, like sine and cosine, but from negative pi on 2 to pi on 2. And it has length pi, not 2 pi, so we need to keep that in mind. So to find the solutions for this equation, I'm going to say theta is equal to tangent inverse of 2, because this is not a nice coordinate that I'm used to, like square root of 3 or square root of 2 over 2 or 1 over 2 or anything like that. This is just some number that I'm going to need the inverse trig function to help me with, the calculator to help me with. So theta is approximately 1.12 radians, which is roughly here. Now, where else is tangent going to be positive? Down here, right? Down here in the third quadrant. But this is outside the range of tangent. The domain of tangent, actually. It's outside the domain of tangent. So this is not relevant for this problem. Okay. So, tangent's only going to yield one answer here, or one base angle. But we still do need to say theta is approximately 1.12 plus, not 2k pi, but k pi. Not 2 pi, because tangent repeats every pi, not every 2 pi. That's why we're only adding multiples of pi. Because tangent has period pi. Period of length pi. Okay. So let's talk for a second about why sine and cosine have been yielding two answers, or two base angles, and tangents only yielding one. If I graph sine, oof, so 1 to negative 1, and then here's pi, and 2 pi, 3 pi, negative pi, negative 2 pi. So if I graph sine, something like this, and the graphs of sine and cosine are pretty similar, so I'll just graph this one example. And I ask you, so this is sine theta. And if I ask you, where is sine equal to 1/2? So where does it give me an output of 1/2? Well, think about this one period of sine from here to here. So this first period of sine from 0 to 2 pi. Isn't it going to hit this 1/2 here and here? Right? It's going to have two solutions within this one period. Sine and cosine will both do this just because of the nature of their graphs, except for those points at 1 and negative 1. See how it'll only, if I ask you when is sine of theta equal to 1, it'll only happen one time, just right at the peak per period. Now look at the graph of tangent. It's something like, oh no, well, that wasn't terrible, but okay, let me draw my asymptotes first. So here's one period of tangent. So it does something like this, and like this. There's tangent. So if I ask you, for instance, where is tangent equal to 1/2? So if 1/2 is roughly there, it's only going to happen one time in this period. It's not going to hit twice. The sine and cosine graphs will hit twice, but this will only hit once. That's why sine and cosine are going to yield two different base angles within each period, whereas tangent is only going to yield one base angle per period. Okay. So let's get into, let's get into solving trig equations that aren't yet explicitly solved. The trig function itself is not explicitly solved for. So we're just finding all solutions to this equation. Just still finding all solutions, just like we've been doing the whole time. Well, the first thing you're going to want to do here is isolate the trig function. Isolate the trig function just by solving for sine theta. So I'll say 2 sine theta is equal to 1 just by adding 1 to both sides, and then sine of theta is equal to 1/2 just by dividing by 2 on both sides. And there we go. That's it. This part is not the tricky part. The tricky part is then going from this to the angles that satisfy this equation. But this was actually the very first example we did, sine of theta equal to 1/2, and we got that theta was pi on 6 plus 2k pi, and theta was 5 pi on 6 plus 2k pi. Okay, let's try another one then. Let's see. Tangent squared theta minus 3 is equal to 0. So I should keep in mind that tangent has period negative pi on 2 to pi on 2. So in the end, I'm not going to add 2k pi, I'm just going to add k pi. Just single rotations of pi, not full rotations of 2 pi. I shouldn't even call them rotations because pi is not a full rotation. Anyways, the period is pi, that's the point. So over here, solving this equation, I'll have tangent squared theta is equal to 3. And then tangent of theta is equal to plus or minus square root of 3. So adding the 3 to both sides for this step. And then from here to here, taking the square root on both sides to get rid of squared. Okay, so now I have two equations. I have tangent of theta is equal to square root of 3. And tangent of theta is equal to negative square root of 3. And since now I know that each tangent should yield one collection of solutions, I should expect two collections now because I have two separate equations. Okay, so where is tangent of theta equal to square root of 3? Well, that's one of those nice angles, or nice coordinates rather, for tangent. That's going to be square root of 3 and 2. This angle is pi on 3, and this works because tangent is opposite over adjacent. That would be square root of 3. So this is theta equal to pi on 3 plus k pi. There's one of them. That's for this equation. Where is it negative within this bound, right? It needs to be within, negative pi on 2 to pi on 2, and I found this one. So where's the other one where tangent will be negative? Well, it's got to be down here, right, where that is that is the 5 pi on 3. So this opposite side is negative square root of 3. This adjacent side is still 1. Hypotenuse is 2. So I'm getting that theta here is 5 pi on 3, and then plus k pi. But this is not quite right. This is that angle, right? It's 5 pi on 3. That's fine. But I need to stay within the bounds of the domain of tangent, so I can't call it 5 pi on 3. I need to call it negative pi on 3. I need to go this way instead of all the way around so that I can stay within the domain of tangent. So these are actually my two solutions. This is not a legitimate solution, even though by its location it's the same, but tangent has a restricted domain, so I just need to name the angle as a negative pi on 3 instead of 5 pi on 3. And that's just because tangent is picky about its domain. So I got two answers here from the two different equations. Two collections. Tangent of theta equals square root of 3 yielded this collection. Tangent of theta equals negative square root of 3 yielded this collection. Okay, now we're going to get into some factoring of trig equations, which sounds scary, but it's not that bad. So still solving just solving the trig equation, find all solutions is the instructions. And we're getting 2 cosine squared minus 7 cosine theta plus 3 is equal to 0. Okay. Now the idea with this is that this is a quadratic function in terms of cosine. We've got cosine squared single cosine and then a constant, and I want to solve for the zeros of this, just like I would a regular quadratic equation. And what I can do to make myself more comfortable is I can let x equal cosine theta, and then rewrite this as 2x squared minus 7x plus 3 is equal to 0. And I can just solve for x using pre-calculus techniques, and then in the end I'll replace x back with cosine. And then I'll still have work to do from there, but to solve this quadratic equation, I'll write it in terms of x, just to make it look much more familiar. But these really are the same thing. It's just that x is playing the role of cosine theta here. Okay, so how do I solve this? So I could factor it. I could use the quadratic formula, whatever method you're most comfortable with. It is factorable. It is factorable, and it'll factor into, let's see, I need two numbers that multiply to give 6, that add to give negative 7. They've both got to be, it's got to be a negative 1 and negative 6, but this is a grouping problem, so it's a bit more complicated than that. Anyways, I'm just going to try to, I know that this is 2x and x, and they both should be negative, and I'm just going to try and figure out what these should be, just by kind of looking at it. Let's see, I think this should be 1, and this should be 3, because this will give me a negative x. This times this will give me a negative 6x. There we go, that'll add to give me negative 7x. And this times this will give me positive 3. Okay, so this is it. Now I split them, and I say 2x minus 1 equals 0, and x minus 3 equals 0. Solve each one. This one will give me x is 1/2, and this one will give me x is 3. Now replace x with cosine theta. So cosine theta is equal to 1/2, and cosine theta is equal to 3. Now, cosine of theta is equal to 1/2. We've already done that one. That gives us theta is equal to pi over 3 plus 2k pi. And theta is equal, it should give us 2, right? And it is 5 pi on 3 plus 2k pi. Over here, this is undefined, no solution. Why? Because the range of cosine is from negative 1 to 1. So if okay, so yes, cosine of theta equal to 3 is undefined, has no solutions, because the range of cosine is negative 1 to 1. This is also works for, well, before I say that, this is our answer here. But this is also true for sine. So, for example, if I asked you what's sine of theta equal to 2, this is undefined with no solution, because the range of sine is also negative 1 to 1. That's not true for tangent, though, right? Because we worked a problem with tangent equal to 2, but the range of tangent is undefined. The range of tangent is undefined, right? Its y values just go off to infinity and negative infinity. So I could ask you what's tangent of negative 45 or something like that. But for sine and cosine, the output, for there to be an answer, the output has to be between negative 1 and 1. Okay, so part B, so it's again a factoring type problem. 4 cosine squared theta minus 4 cosine theta plus 1 is equal to 0. So let's again let x equal cosine theta. So we have 4x squared minus 4x plus 1 is equal to 0. And then we want to factor this and solve, and this is one of those perfect square trinomials with 2x minus 1 all squared. So you can factor that by whatever method you're most comfortable with, but eventually you'll get 2x minus 1 times 2x minus 1 is equal to 0, so, or 2x minus 1 all squared. So this is just going to yield one solution here, because I can, these two factors, 2x minus 1 and 2x minus 1 are the same. In other words, I can square root both sides and get rid of the square, and I just end up with one solution for x, which is going to mean that I have cosine theta equal to 1/2, so just one equation, and I've already solved this one. This one is cosine theta is equal to 1/2. That's pi on 3 plus 2k pi. Theta is equal to 5 pi on 3 plus 2k pi. Okay, so that one's much quicker because we've already solved this equation. Okay, number 8, or page 8 rather. Example 7 is another factoring problem. It just looks a little bit different. Factoring to solve 5 sine theta times cosine theta plus 4 cosine theta is equal to 0. So this is not the same kind of factoring as this, because this is a quadratic equation in terms of cosine theta, but this is not. This is got sine and cosine involved. But can't I factor a cosine out of each of these terms, leaving me with 5 sine theta plus 4? And now I can split these two equations because I have a product. This times this equal to 0, so I can say cosine of theta equal to 0. And 5 sine theta plus 4 equal to 0. This, where is cosine theta equal to 0? Where is cosine theta equal to 0? Well, it's equal to 0 here and here at pi on 2. And I'll say plus 2k pi to get every rotation, and 3 pi on 2 plus 2k pi. So that's for this equation. Now what about this equation? Well, I've got sine of theta is equal to negative 4/5, just by solving for sine theta, subtracting 4 and dividing by 5. And then this is going to be sine inverse of negative 4/5. Why am I solving it this way? Well, because 4/5 is not some standard coordinate that I know about, like square root of 3 or 1/2 or anything like that. So I've got to solve it this way using the calculator, and I get that it's approximately negative 0.93 radians, which is roughly down here somewhere. And where else is sine going to give me a negative answer? Well, it's got to be down here. So I will do, if this is negative 0.93, then how do I find this one? I'll do pi minus negative 0.93 to find this angle. In other words, pi plus 0.93, and that's going to give me 4.07 radians. Okay, so my two solutions from this equation are theta is approximately negative 0.93 plus 2k pi, and theta is approximately 4.07 plus 2k pi. So each of these equations yielded two answers. Here's the two answers for cosine theta equal to 0, and here's the two answers for sine theta equals negative 4/5. And that is it for this section. Much shorter section. And it should seem easier in the sense that a lot of the techniques we're using to solve these equations we've already looked at, like the inverse trig functions and finding angles, like corresponding angles. If this is negative 0.93, where else is sine negative? You know, we've done things like this, finding angles in other quadrants and things like that. So it should seem a little bit more familiar than the past two sections. But that is it.